Welcome back to the lab, and this is the hydraulic trainer that we're going to use. It's the LabVolt. I can turn it there a little bit so you can get a better look at it. So here we have the pump unit. This pump unit is a complete unit that has its own filter, its own pressure relief valve that's internal to the pump and the reservoir. And you can see there that we have the schematic diagrams for both. So right here is the pump outlet and the tank inlet. So this device will have oil cycle through it. What we're using here in this first lab experiment, and that's the one I included in the notes package, is we're going to lift this big heavy unit with a 1-inch cylinder from the rod end, which is the end that has less pressure, of course, than the cap end. Now, it says in the instructions to be careful to not set this down on your feet, and they actually wanted this turned around backwards, but I figured I'd turn it this way so you have a better display of it. I'll just remember to keep my feet out of the way. On the tank end, we have a manifold which allows us to bring two lines back to the tank in parallel, and that simplifies things a lot. Here we have a pressure reducer, and it doesn't call for that in the first part of the experiment, but it does in the second part of the experiment. Well, I thought I'd just cut to the chase. So what this thing does is it reduces the pressure below what it is coming out of the pump. Now remember, the pump has its own internal pressure regulation. This can reduce that pressure further by taking the excess pressure and moving it back to the tank. Next to that, we have our directional control valve. This is a closed center directional control valve, so that means when I'm finished triggering the device, it will stay in the position that it was last at. So I can stroke this halfway, 3/4 of the way, just touch it. And this is the type of controller that you would find on an excavator or a farm implement, something along those lines, where I might want to set my bucket angle or the angle of my arm. And of course, it has pressure coming in from this pressure manifold here, and this manifold allows me to parallel my lines up. So really the reason this is here is to give you the pressure gauge and also the flow meter. Now the flow meter is calibrated in liters per minute flow and gallons per minute flow. Your pressure gauge is in the black, is in pounds per square inch. The red in this interior is in kPa, and remember that 1 bar is approximately 100 kPa. So I look at this as 10, 20, 30, 40, 50, 60 bar. A bar is an atmospheric pressure. So 60 atmospheres would definitely squish you like a bug. So the last thing we would want to have is high pressure fluid coming out of any of these connections. It's really important when you're setting these connections that they are tested to make sure that they're 100% connected. If they're not, the hose can blow off when I energize the circuit, which, even though there is a check valve in the end of these, some fluid can come out and it can whip with a substantial amount of force, and if you're anywhere near it, that can be an issue. Okay, so I'm gonna demonstrate how this works. So I'm gonna finish putting on my PPE. You'll notice that I have on steel-toe boots. Oops, put the camera this way. Steel-toe boots. And I also have on my safety glasses, which is extremely important because any kind of high pressure fluid in the eye would, well, not too many blind electricians out there, just saying that. I'm going to use the wonderful latex gloves. They will provide a barrier between my skin on my hands and the fluid itself. The fluid can be carcinogenic, so it can cause cancer over long-term exposure and other health effects. Plus two, if I have cuts on my hands, scrapes, abrasions, the fluid getting in there can cause some secondary infections. And in today's world, a secondary infection is something you definitely don't want. Okay, so let me just turn this on and we'll show you how it works. So turning on the pump, the fluid is pressurizing the system, and the excess pressure or the excess fluid will be internally encircled inside the pump and this reservoir unit. I can use my pressure control valve, my pressure reducing valve, to reduce the pressure below the set point. And you can hear that as it starts to whine, as that goes through its cracking pressure to its full open pressure, allowing fluid to go back to the reservoir. Just to give you a close-up of that. Try very carefully not to make noises with the camera. Okay, so you can see as I turn the red button, I can increase or decrease system pressure, but I can't go above the pressure that the pump will put out due to the internal regulation. So that's why it's a pressure reducing valve. It's reducing from a set high pressure. So there, my maximum pressure on this system is approximately not quite 40 bar, not quite 40 atmospheres, about 38 atmospheres or 3,800 kPa. 550 psi for you standard measurement folks. Now I can drop this pressure, system pressure, quite frankly, all the way down to 0 by using the pressure relief. Well, not quite to 0, but pretty darn near. I can reduce this to 5 bar or about 500 kPa, because you will have some production of pressure due to the restrictions in the lines. So we're going to start it here at 30 bar, which gives us a wonderful noise. So I might pull that up a little bit. Let's go to maximum circuit pressure, and that'll give us the least amount of noise on there. Okay, so as mentioned, this is a closed center valve, so nothing's happening right now. As I retract the valve, I can raise the load, and you see as I let go of the joystick, the load stays exactly where it was, right? And I can throttle that in both directions. Okay. Now, you'll notice that it drops a lot quicker than it raises. Two reasons for that. The big one being gravity, and the fact that the load is working with gravity as it goes down and against gravity as it comes up. Not only that, this end right here, the cap end, has more area that is exposed to the same amount of flow, quite frankly, so that is going to develop more force driving down. So really, if the cylinder was the other way around and we were pushing up, it would be a more efficient system. However, it still works. Now, we can calculate how much force is required to lift this reservoir, and indeed then extrapolate the weight off it by timesing that by gravity, if you're really bored and you want to figure that out. So what we're going to do is we're going to drop the pressure, the system pressure below, and see where we can actually lift the load. So let's drop it down to 20 bar, 2000 kPa, and you'll see that I have flow in my system now where I didn't before. That flow is due to the fluid going back to the tank, right? And you can hear the whining coming from the pressure relief valve, or pressure reducing valve, sorry, my mistake. I got the two mixed up a lot. That's the electrician in me. All right, so I'm gonna stroke this backwards to try and lift the load. Oh, she tries to lift the load, but it can't do it. The reason it can't do it is it doesn't have enough force to overcome the gravity and the amount of force pressing down by gravity. Okay, so at 20 bar, we don't have enough force to lift that load. So let's turn that up a little bit. Let's go to 25 bar. Now you see you're getting a little bit of a dancing gauge there, and that's due to the fact that that spring and that ball on that pressure reducing valve are kind of trying to cycle between that cracking pressure and that full volume pressure. So it's bouncing back and forth. And that would be very annoying in a circuit if you were trying to position something very delicately. This would be a great place to put in an accumulator to help absorb those shocks. Okay, let's try her and bring it up, and that's enough to lift our system. No problem at all. Now I can control the speed of this by being my own speed controller by just cracking the spool valve ever so slightly. And what I'm doing there is I'm restricting the flow through the directional control spool valve. As a result of that, I can control the speed of the cylinder. All right, so that is enough to keep it going. So let's just drop this a little bit. Let's go down to, we'll call it 22 bar, 2200 kPa, and see what happens. Oh, not quite enough. It tries and it develops it, but it can't quite do it. Okay, so let's just increase the pressure here somewhere. Let's just go right back to maximum system pressure that the pump in the unit can provide. And this will give us an idea of the amount of flow we have going through the system on each stroke. So as I pull the directional control valve back to lift the cylinder, you'll see that my pressure goes down and my flow goes up because I've given a path for the fluid to flow through. As the fluid flows through, of course, the pressure built up behind that closed restriction is alleviated and my pressure gauge drops. As soon as the work starts to happen again, that pressure gauge comes back up and that flow drops off. A pump will only work as hard as it has to do the job. And that's an important thing to remember, all right? So you're limited. So let's take a look at what we have for full stroke flow. Oops, drop that back down there, okay? So on the upstroke, which is using the small rod end of the cylinder, which has less area, let's see what we get. So we get just about 2 liters per minute, maybe a little bit more at system pressure. Now as I drop this load, and I won't retard the speed, I'll just drop it straight up, boom, and you see that I get about 3.5 liters per minute due to the aid of gravity and due to the bigger area. So I have a longer flow and a bigger flow, even though the hoses are the same size. Okay.